In this question, we're given a table which shows the amount spent per month by a car dealership on their marketing and advertising, and the number of cars that they sold that month. Let's be careful. The M variable, the amount spent on marketing and advertising, is in thousands of pounds. So the 6 is 6,000, and then we have 7,000, 8,000, 9,000, 10,000. Part A of the question asks us to use the statistical calculator to find the value of the product moment correlation coefficient between M and C. The PMCC, the product moment correlation coefficient, is usually denoted with R. We're looking for the R value, the correlation value, the strength of correlation between M and C. We do this on our calculators by putting the M values into list 1, the C values into list 2, and then we go through to the regression, summary statistic mode, and there we have it right in front of us. R is 0.7555. Part B of the question. We're asked to find the equation of the regression line between M and C and to give it in this form. Well, the constants A and B are still on our screen. A for this data is 2.8 and B for this data is 1.1. They go into the formula just like this. C equals 2.8 plus 1.1 M. And this is the formula, this is the regression line that we can then use for any predictions or estimates we might be asked to make. Part B of the question says to use the equation of the regression line to estimate the number of cars that are expected to be sold in a month where the amount spent on marketing and advertising is 8,800. Be very careful here, big mistake. A lot of students will substitute 8,800 into the formula. We've been told that the M value is thousands of cars. So we have 8.8 thousand cars. That's the number that needs to be substituted, and we get 12.44. So we'd expect 12 cars to be sold. What about when we have 20,000? We're substituting 20, and that goes into the formula to give us almost double, 24.8 cars to be sold. Okay, so just substituting each of those into the formula and evaluating the result. We are also asked to comment further on the reliability of each of the two estimates. In the first case, we substituted 8.8. In the original dataset, the value of M went from 6 to 10. So we can be fairly confident that any substitution in between 6 and 10 will be reasonable. That would be interpolation. So we have a reason to be confident in the results. Interpolation is reliable. On the other hand, we've substituted in 20. Well, this data set never reached up to 20 in the first instance. This is not interpolation, but extrapolation. So we've made a prediction outside of the original range of the data. This is extrapolation, which is risky and it's unreliable. So there's my two comments on the reliability. Interpolation is reliable, extrapolation is not. In part C, we're asked to interpret in context of the question the physical meaning of A and B. So when we look at the formula, A, the 2.8, well, that's going to be the y-intercept. But that's not what the question wants. We must talk in the context of the question, in the scenario of the question. So talking about cars and the amount of money you spend on advertising. Well, the y-intercept is going to be the number of cars you would expect to sell if you had no money spent on advertising. So without any advertising, this is what you would expect. That's the base rate with no advertising. Well, B is the gradient. And yes, mathematically, that's what it is. But once again, in the context. So you wouldn't get any marks for y-intercept or gradient. We need to describe them within this scenario. The gradient is the number of extra cars you would expect to sell for every £1,000 spent on advertising. So remember, even though it's 1 unit increase of M, each 1 unit of M refers to £1,000 worth of advertising. So those are the extra comments that would get you full marks on this question.